Really excited today to have Jia-Bin Huang. He is an assistant professor at Virginia Tech, and prior to that, he got his PhD from UIUC. And he does a lot of really cool research at the intersection of computer vision, computer graphics, and machine learning. And so he's gotten a lot of different paper awards and other funding awards, as well as if you're in the academic Twitter sphere, I'm sure you've seen his work. He's had a lot of really cool work on 3D depth in painting and view synthesis. So I'm really excited to have him today talk to us. I know it's going to be an exciting talk. So with that, Jia-Bin, take it away.
All right. Okay. Thank you for the introduction, and thank you all for attending my talk. So today I will talk about some fun topic. I know this is the last session in the ML seminar at Georgia Tech, so it's going to be fairly relaxed. So, and please feel free to interrupt me at any time if you have questions. And I'll also stop at part of my talk. I will stop there and then ask questions if you have any. Okay, so let's get started. So, if we think back how photography looked like over a century ago, it has really come a long way. So this was the first photograph that was ever taken in 1840s. At that time, photography was very expensive and it's a time-consuming process. But the image quality is still very poor, as you can see from this photograph. So 100 years later, so the quality has improved dramatically. This image was taken in 1940s, when the color film was first introduced to the market. And we fast forward for another 30 years, we see even more improvement. So, but the photographs here, you still see that it has relatively low fidelity. So it's not really reflect the real world. And that changed with digital photography, which brought us high fidelity, high resolution, and vibrant colors. So the pictures we have taken here is very great. So, and amazingly that today we can actually take photographs that's just as good, if not better, with cell phone cameras in our pocket. And so now photographs now allow us to capture memorable and share memorable moments of our lives. So, so this is a photo that was taken in 2018, and photography can also be used to visualize how time flies. So this is a photo we taken this year. All right. So, driven by the passion about photography, over the past few years, I've worked on several projects to use computational techniques to overcome some limitation of traditional photography. So the goal is to improve the way we capture, process, and interact with visual media. For example, we developed algorithm for removing and filling plausible pixels for images or for videos. We want to recover the high frequency information from the low frequency one, so super resolution problem. We can also recover the high dynamic range image from a typical low dynamic range image input. Also develop algorithm for learning the mapping between two images from two domains, like summer, winter, or different cats and dogs. Or we want to make if we apply this image-based algorithm independently for the video, it will be flickering, and we can improve this consistency over time for videos. So with all these advances, there's still a couple of things that I'm not satisfied with. So that's something that I want to talk about today. The very first thing is that the 2D photography are essentially flat. What it means is that no matter where my viewing angle is, the photo look pretty much the same to me. We don't see the motion parallax we experience in the real world. So, as we discussed earlier, 2D photography now already has remarkable image quality. So how can we make this even better? So the first part of the talk, I will show you how we can convert these plain 2D images into something we call 3D photos. And our generate result like this provides dramatically more immersive experience than the 2D image counterpart. Okay, so that's the first part. And the second part of the talk, I'll show you how we can extend this to video. So video is great. It's a window to another world, but the viewer does not have the control, does not have the power to control the viewing directions. So you can only see this from this perspective. So in the second part of the talk, I will show you how we can, our recent effort to enable 3D free viewpoint video and advanced visual effects. Okay, so I hope that I will have time later on. So these are the two works that focus on visualizing new ways of visualizing images and video. So if I have time later on, I will show you how we can edit the image and video to make your image or photographs or videos better. Okay. So specifically, one particular like problems I really kind of obsess about is that I always feel frustrated taking photos through fences and windows. So this happened a lot when I take to the kids to the zoo. We see that you see kind of obstructions from your photos. So this is not, it's very hard to get a clean shot, but this is not how I remember the scene, how I remember how awesome the tiger was and how I can read the text from the through the reflection. So in the last part of the talk, I will show you how we can use computation techniques to recover the clean image. Okay, we can get a result like this. All right, so we call it abstraction free. All right, so that's the plan of today's talk. Okay, let me dive right in about 3D photos. So this is the problem. It's known as single image view synthesis. Given a single image as input, the goal is to be able to render the same image from a novel viewpoint, like this one here. So there are a couple of challenges involved in this problem. First, you need to understand the dense depths. You need to know where each pixel, how far away each pixel is from the camera. For example, here we know that the boys is closer to the camera than the tree behind, so that we know how much we should move a pixels when we view at a novel view. Okay. The second problem is that when you render a novel viewpoint, you will see the seclusion because those are the regions that are not visible in the original viewpoint. Right? So you'll see like large area of the seclusion that breaks down this photorealism. Okay? And the third problem is that you will need to model some view-dependent effects. Right? So there are a couple of goals related in this particular project. Right? So the first one is that we want to work with single image input. We don't want to work with multiple images because it's very hard to capture that, and it's only limited to static scene. We want to work with any photos, which means that we want to be not just for images in a closed domain like driving scene or images of bedrooms. We want to work with a variety of different photos in the wild. Also want to have a compact representation so that we can efficiently render the image on something like low resources, like for example, a mobile camera, a mobile phone. And the last goal is that we want to have a consistent viewpoints. What does that mean? It means that when I render the novel view, all the seclusion will come out consistently in a consistent manner. Okay, so we hope that our project hits all of these goals. All right, before I talk about our own method, I think it's important to talk about what kind of 3D representation we can use. There are many alternatives here, but not all of them are suitable for our goals. For example, light fields store many views of the scene and interpolate them to create novel views. This allows us to create a very realistic appearance, but it has excessive storage and memory requirements. So you need to capture many different views in order to interpolate them smoothly. You can also represent the image by estimating the depths so that you can represent this as a 2.5D representation. So you can have a 3D point cloud representation. And when you render a novel view, you basically project this 3D point cloud onto this novel view and then followed by impending algorithms, okay, impending some missing regions. However, this is very computationally expensive because you need to have a GPU at runtime for every single view. Also, it's unable to generate view consistent results because for each novel view, you need to process this independently. Yet another representation is called multiplane images representation. So this represents a stack of frontal parallel RGB alpha textures. So this representation has been fairly popular in the community of view synthesis because of its regular structure nature, which makes it suitable for using it in the CNN. So it's very easy to use, but it's not very storage efficient. So you need to store many different empty space. Okay, so it's not very easy to use this in a fixed mode. View this on a mobile phone. So the particular representation we use instead is called layer depth image, or LDIs. So this is an interesting representation. This essentially is an image where each integer pixel position you can store one or multiple RGBD values. Okay, so the XY image coordinates are quantized just as the image normal pixel grid. And each image coordinate corresponds to a 3D ray into the space. And this particular one I'm showing here has 3 LDI pixels. Unlike XY image coordinate, the depth of the LDI pixels is not quantized and can store arbitrary floating points values. So it can model this scene geometry very accurately. So there are a couple of advantages about this representation. First, it's sparse. So we only need to represent the geometry of the scene where we need it and nothing more. It has flexible topology, so you can store like very complex, complex scenarios, but locally looks like an image, so it's good for algorithm. And it can be efficiently converted to texture mesh, so you can render this efficiently. Right, so that's kind of the main advantage to suitable for our goal. So how does our method work with this representation? Let's first look at the problem of depth space swapping. So if I have an image, we can estimate the depth either through stereo or through a monocular depth estimation methods. If we render this view image through the depths, you will see something like this. You'll see that edges across the depth discontinuity, you'll see the texture are stretched severely. So this is the problem because you see these strong artifacts. So how do we fix this? Okay, we can say, let's just discard all these meshes, and you end up with something that's whole. Right? You have some missing regions that you don't know what those pixel values are. Right? So the idea is very simple. Let's just fix, because we have this problem, so let's just fix this with a layer depth imprinting algorithm. So how does this work? Layer depth image imprinting works. So imagine that let's look at a simple toy example. Like if you zoom in to a step edge in an image structure, you'll see something like this, right? So on the left is further away from the camera, on the right is closer to camera. So you first at the beginning, every pixel is connected to its 4 nearest neighbor, and you can first cross the depth discontinuity to remove those meshes. Then you can identify, the next step is to identify where the background context should be. You identify some region that's where I can borrow these are the source regions I can borrow the content from, and also identify where I should impend the regions. Okay? And then I can impend the color as well as the geometry of this missing region, these red regions. And then now we get the multiple layers of representation. Okay? And you can do this for many different local areas. Then you will have a complete, when you won't reveal any holes when you render at novel views. So it's a very simple algorithm. Okay. So the one crucial difference between LDI-based imprinting versus image imprinting is that LDI imprinting has like adaptive context and it's local, compared to the image imprinting, which is global use static context. Every known pixel is a context. So this is important because every time the source regions you want to use are different from one depth H to another. Okay. All right. So let's zoom out a little bit to see how everything fits together. So given an RGB image as input, you first estimate the depths. We see that the depth usually depth estimation is not perfect, so you will smear out the depth H. So we use a simple filter to fix that. So to have a sharp depth H. And then you can identify some post-processing to identify the depth connected depth edges to form a long track of depth edges. And then you can identify several sub-problems. Like for each depth edge, you have a context region and a synthesis region. All right. With this, you can start the impending process. Okay. So the impending process is actually very simple. You can use whatever impending algorithm you want. You have color, depth, and edges. You first pick a subproblem that is, I want to impend what's under the leaf. And what I can do is to, instead of just impend the color and depth jointly, independently, you will end up with inconsistent color and structure. So what we did instead is to impend the depth H first, and then use this depth H as a guidance for color impending and depth impending. So this will help us to maintain the same structure when we recover the missing appearance and geometry. Okay. All right. So before I show the result, I want to talk about some of the consideration in training data. How do we actually train this? So existing work usually use synthetic data set to training because you can render arbitrary viewpoints, so you can train this very easily. However, it's unclear how we can transfer the ability of view synthesis from synthetic data set to real world scenarios. So what people usually do instead is to collect data from real world. However, it's very difficult to get the accurate geometry of the real world. So what do? The next best thing you can do is to collect something called post-image datasets. What this means is that you have the same thing, but you have multiple images, and you can somehow estimate the camera poses of the same thing, either through structure from motion algorithms or some special hardware. Okay, but this is fairly limited. Either it couldn't scale or it couldn't really capture dynamic things. I actually tried to collect this post-image dataset on my kids, but it turns out it's very challenging because they never stop moving. They keep moving, so there's no way that you can really capture such post-image datasets. Okay, so instead of doing this multi-view image dataset, we went for single view image dataset, which means that I only require a single image to train our models, but I can train the model to perform multi-view synthesis. All right, so how do we do this? So the idea is very simple. I take something like a COCO dataset where we have diverse thing, and then you estimate the depth and pretend that the depth is ground truth. You estimate the depth through some molecular depth estimation algorithm. You can identify some of the missing some of the depth discontinuity, could create a pool of occlusion patterns. What are the type of occlusion naturally occur in images? You then copy and paste, randomly sample, copy and paste these masks onto other images. And because in other images you have the ground truth RGB and pseudo ground truth depths, you can learn your image impending model, saying that here is the context, and please synthesize this region, the RGBD of these regions. Okay, so this is a very simple approach. That's synthetically generated data set, but it works because we can train this in a very large scale, so it turns out generalized very well on a variety of different things. All right, so let's take a look at some results, some images to see how well this can work. Oops, my PowerPoint just died. I need to restart. Okay. Right. Sorry about that. All right. Hopefully, can you see that? Can you see this?
Yes, we can.
All right. Okay. Awesome. Okay, so let's see some comparison. So we first compare with some method that use multi-client image representation. This method take two images of narrow baseline as input. Typically, these two images could come from this kind of stereo camera from your cell phone, and they want to produce MPI. There are several different methods that enable this using these algorithms. So we compare with all of them on some dataset they collected. Real estate 10K. So these are indoor data sets. So you can see these are the results comparisons. So in general, our method has fewer artifacts than the others because we explicitly deal with the seclusions in using these problems. All right. So we can also do quantitative comparison. So this is we test this on the real estate 10K from the stereo magnification paper. So the way it works, the way that we can evaluate this is the following. So we have a video of some footage from internet of some real estate, and then you can extract the camera trajectory through some structure for motion algorithm because everything is static, and you then take samples 2 frames from that trajectory, 2 frames from that trajectory as input, and you ask the method to produce that target view, and at the same time you have the target view ground truth, so you can evaluate this. So we show that we can our performance is better than the others and comparative to these 2 view based methods. Okay, but our method is essentially still a single view algorithm. So it's more exciting to see what it can do on images in the wild. So here are some visual comparison with state-of-the-art single view image using this algorithm. So let's watch the video. All right, so that's cool that we showed that our methods can perform better compared to others. But I think the most exciting part of our method is not really beating other algorithm. Is that we can actually apply this to any photos in the wild. So to demonstrate that, I put together a fun family videos using my own family photos that taken in the wild. So let's enjoy it. All right. So because it all work with single image only, and it can work with on a wide variety of domains. So we can actually, this is something that I found very exciting, is that we can actually use our method to go back in time and visualize the history in 3D. So here is the video. All right. So I think this really helps bring the visual memories to life. And since we put this out, and it's actually we are currently working with two documentary firm directors, and they will be making documentary films by adding these visual effects. So hopefully you'll see that in HBO soon. Okay. So in addition to this kind of just typical like boring 3D viewpoints, you can actually play around with the cameras creatively. For example, one cool thing we can do is to create dolly zoom effects. So creating these effects through like actually capturing this effect is not easy because it needs to change the focal length very carefully while you move the cameras forward, either closer to or further away from the main subject. But you can do this very easily with just single photo, and you can create something like this. Right. So we released this the code and demo online, and at some point, I think in April, it reached like probably I think we got like 3 million views of web page views. So it has reached to a lot of people, and we have seen like many creative use of our methods from the communities. For example, here is just some sample of some Twitter user that they take our method and apply their own domains. So this is like they take the historical Titanic interior and then create this kind of virtual fly-through tool to this historical site. People use this to create interactive comic books fly-through. So this is a comic book illustrations. People can use this to create an interesting effect for this perspective arts. Can use this to this is, I don't know what this is. This is a synthetic image, and then they create this kind of scary things. And then you can visualize arts in a different way. You can create movie poster, and this actually is currently applied commercially and from a streaming service. And we can also create this visual effect for anime. So people also try different ways of visualizing these 3D photos. So for example, people use this instead of using the screen, your cell phone, you can create this hologram. And some people create this interface where you can have a Chrome plugin, and you can browse through Instagram. You can click and turn every photos in the Instagram into 3D. All right, so all these are cool, but it's still not perfect. So what are the failure cases? So we couldn't deal with thin and complex structure very well yet. So you see that you'll see artifacts when your scene has certain thin and complex structures, especially hairs and tree branches. That's especially hard. And our representation does not deal with transparent or reflected surface, such as you see the reflection here. They're physically incorrect. because of the use of depth map. Also, when we apply this to domains that's not trend on, for example, this R domain, we find that the impending algorithm does not work very well to realistically impend the missing regions. Although this guy should stay home and save lives. All right, so far we only talk about 2D images to 3D photos. And this year we also have a fun project that asks the question: can we draw a 3D photo? Like just imagine a 3D photo out. And so what we can do is that we ask user to draw some semantics label maps, and you can create 3D photos out of that semantic label map. So this leverages the structure of this semantic and relationship with the geometry. All right, so I want to put a mini conclusion here, stop here, and see if there's any questions about 3D photography before I move on to 3D video.
So there are two questions for you. Both of them, they are like, this is awesome work, which it is. But the first question is, how well do you think this can work on Google Streets imagery and possibly convert that into much better city tours or campus tours? Will it work just as well on that?
Yeah, that's a good question. So for city, for this Google Street View, I think they already can do something better. So here we focus more on single image cases where you only have single image, like historical images. You couldn't go back to the moon and take multiple pictures. So, but for Google Street View, that application scenarios, they already have multiple images they capture, so they can potentially estimate better depths, estimate better geometry, and they can fill in the seclusion much more reliably. The challenge there is that when they drive through the city or drive through the campus, the world is not static. So you will see the car like on one image, and the car will move. So for that, it's going to be a challenge in the reconstruction to deal with dynamic objects. But I think that's definitely exciting application. So I think either Google or also Apple is working on that.
Awesome. And there's another question also about applications, is they just want to make sure they're understanding this correctly, that the input is a 2D image and the output generates the sort of 3D image. Can you describe what applications this would be useful for?
Right. So the input is just a single image, 2D image. There's just a couple of applications. So I can comment on some application that people already pick up. There's documentary firms already are using this for creating a HBO documentary firms. There's like when you do this kind of streaming service that people use this kind of movie posters, and they use this to create much more engaging content, so they kind of get your more attention to the images and videos. Just images. There's also some other usage that I saw from the internet that they use museum. They take this and then create this monitor and a poster so that you can actually. I think this is an insect museum. So in Japan, they take this and create this 3D photo, and they can track your viewpoint and then create this kind of 3D insect to attract this educate younger generations. So I think there are a lot more potential application that this can be.
Awesome. A couple other questions have come in, but we'll save them to the end if that's okay.
All right. Yep. Sounds good. All right. So this is about images, but how about video? So we capture a lot of videos nowadays. So how can we create similar capability of video? Wouldn't it be cool if we can take self-capture videos and create visual effects like these ones here, like depth-aware effects, fully automatically? So to do so, we really need to understand the full geometry of the scene, right? We need to ask a consistent dense depth map of the scene. Okay. So how can existing method do this? So structure from motion algorithm, this from COMAT, only estimate depths at very few points. Even dense multi-view stereos has many holes, typically when objects are moving or non-texture areas. So learning-based method recently has a lot of progress. It provides fully dense depths, no holes, but they flicker. So our method can produce detailed and flicker-free depths. So the core idea is to combine the advantage of both geometric-based method and learning-based methods. I will talk about that later. Our method is in fact globally geometrically consistent. So you can actually insert artificial objects and remove them correctly from the scene. So you can also insert 1,000 objects in the scene. So how does our method work? We leverage the data-driven prior in the form of CNN, pre-trained CNN, to estimate depths each image individually for each image. So let's look at two images, just keep it simple. We estimate depths individually for both frames. All right. So if you look at a match point, which you can compute that through optical flow, if you look at the match point, you can see that the depth is not consistent, right? Assuming for a moment that we know the camera pose, and we can measure that with structure of motion, we can project these points via the depth onto the 3D world coordinate. So we can see that the 2 points do not end up at the same location in 3D. So we know the depth is wrong. So the key idea here is to combine this geometric constraint to learning-based method to propagate this error to the network so that the network can resolve a better depth, more consistent depth. So, but it's not that easy. Directly minimizing these 3D errors bias the solution towards small depths, because if you shrink the whole thing into a 3D point, you'll get minimal. You'll get a very small error. So to prevent these degenerate solutions, what we did is to decompose this error into a spatial term, reprojection error, and a disparity term. Okay, so this one you don't have this kind of degenerate solution. And then using optical flow, we can do this for many match points, and the network learns to produce a much better depth for this particular frame pair. So you can actually extend this very easily to the entire video by randomly sample image frame pairs and putting them in a batch. You do backpropagation, then the network learns to estimate highly detailed, flicker-free, and geometrically consistent depths for the full video. So with this, you can actually apply a variety of different visual effects onto these videos. All right, so here I'll show you some results. All right. So this is a great work led by Shen and in collaboration with Kevin, Rick, and Johannes at Facebook. So previously we said that we assume that we have a camera pose. But it's actually a very hard problem if you think about this. So in a lot of videos, in family videos, we typically don't have a lot of camera translation. So traditional structure for motion algorithm actually will have a difficulty in estimating pose reliably. So or like smooth textures or this highly dynamic scenes or like these ones here. So it's very hard. Actually, we try for like using, for example, CoMap, state-of-the-art structure for motion algorithm. It turns out like 60% of the time, it just doesn't work. It doesn't produce any pose for us. So we couldn't really reliably, robustly to estimate depths. So how do we kind of make our algorithm more general? So this is I promise that this is the only equation I'll show in the talk. So let's revisit what the previous artwork, the formulation of previous work. So the objective here is to optimize these reprojection errors. For every pixel p, and for every frame pairs. Okay, subject to some known camera parameters. So if you know the camera parameters, the rotation, translation, and intrinsic and scale, you fix this, right? So let's take a look at this frame pair I and j. What you have is if you have a 2D point in i's frame, and you know the depths, you want to estimate the depth. So you can use this depths and reproject this point onto the second camera j. Okay, so this point basically express this point in the camera coordinate system of the second camera. And at the same time, you have the flow correspondence between these two frames. So you can estimate these points, and you can estimate these steps, so that you know these 2 points do not end up at the same location. So you want to minimize these errors. Okay, so that's basically the overall the method, how the method works. But here you can see that we actually don't know what this is at the beginning, right? So we always, in previous project, we always assume that structure for motion will give us this. But in practice, this doesn't work like robustly. So our idea is to take this formulation, but reverse the role of the depths and the camera. So instead of fixing the camera parameters and estimate the depths, you fix the depths and estimate the camera parameters. All right, so how does this work? So if you have let's use this 3-frame image as an example here. X1, X2, X3 are some 2D tracks of the same 3 points, and assuming that you know the depths. So you can start with this by initializing every camera at the origin work coordinate, and you have some constraint about this point. You know that they should line up in 3D, so you can optimize this to get a new pose for each camera, right? So this resembles the bundle adjustment, but it's a simpler problem because you don't need to estimate the depths. Your depth is you already know. Okay. So, but wait a minute, how do you get the depths? Isn't that the whole purpose of this entire project? We want to get a consistent depth. So we start with this a monocular depth that's fully dense but is flickering. So if we just take this depth as an initialization, so you can see that this is a third-person viewpoint of the scene. If you optimize this with the media depth, because the depth is flickering, so you have some arrow. That arrows will be propagate to the pose estimation. So your pose will be bad. So you can see that the pose is actually not very reliable. So this is because the depth from the monocular depth estimation is only estimated up to an unknown scale. So without perfect scaling, it's going to not look very good. So an alternative is to, let's say we can optimize the scaling factor together with the pose. So this will give us more stable results, as you see here, more stable results. But still, it's very hard to compensate those depth flickering from the monocular depth estimation. So this basically this global scaling methods does not work very well. So instead, what we did is to create a local scaling, spatially varying scaling vectors. And we do this by using a grid of handles to optimize the deformation field. And we use this close-to-fine approach to stabilize this. Okay? So And we also do some post-processing, but I won't talk about this. Let's take a look at some results of this, what this can do. So this is there's an inspiration from the movie Minority Report, where Tom Cruise was watching a video of his son.
My class runs faster than. Look, keep your knees up. Like that. Good. Like that. Like that. Like that. High. Like that. So you're a natural runner. Gotta keep running. Gotta keep running. Gotta keep running. Well, I could be as fast as you someday. Oh, I think you'll beat me someday. I think you'll beat everyone someday. We gotta go. Bye. No, wait. We gotta give me a kiss. Not on the lips. Only Mommy kissed me on the lips.
All right. So in the Minority Report, it says that this will happen in 2054, and hopefully that we can bring this technology to you a little bit earlier. So here are some results of videos depth estimation. You will see the third-person viewpoint, and on the top left, you see the depth map, estimate depth map, and comparison with some existing methods. So here are some results. All right, so this is very exciting because now you can have a mechanism to estimate pose from highly dynamic scenes and estimate consistent depths. So it's as if you augment all the RGB cameras with depth sensors. So with this, to demonstrate the robustness of this, we actually test this on the Davis dataset. So all 90 videos, we can process this, and you see that it's very robust to process all types of depths. So potentially it has implication for other domains such as robotics and navigation for dynamic things. All right, so I don't have much time, so I want to just briefly talk about the disocclusion problem. So we saw earlier, when we render our novel viewpoints, you see the disocclusion, okay, like this one here. So basically, the input video, a boy enjoying his fried chicken, and you see the mesh-based rendering from novel viewpoints. So you see the white areas that are disocclusion. Okay, one idea is to impend this disocclusion using image video compression algorithm, but you'll see that this is not very good because it has this impending. This is very tar. So we turn to this neuron-based neural instinct representation for view synthesis. The idea is to use the multi-layer perceptron to implicitly represent the scene, geometry, and appearance. For this works well for static scene, but for dynamic scene, our first idea is to say, how about just adding a time to this? But turns out it doesn't work because it has this because you can have an infinite number of scene configuration that will match to the input video. So you couldn't really train this to navigate in space and time. So we propose a new method that can regularize this, and we can create this kind of free viewpoint videos so that you can browse through any of videos in any viewpoint and time. So to do this, we want to, specifically the idea is to regularize the depths using the depth estimation network and so this helps us to disambiguate the time-varying geometry and appearance and use a static loss to propagate the missing content across time. So here I will show you a fun video. All right, so I think we're running out of time, so I won't go over the abstraction removal, which I think it's also cool. But if you can go up my website to see how we can actually remove these abstractions from this multiple frames to use the by using this motion constraints. I'll skip most of this, so we can remove these abstractions. In addition to abstraction, I think there's opportunities here to kind of be able to freely manipulate your input video and images to create to remove the things that ruin your memories. All right. So I want to conclude this by some of the exciting opportunities. So I'm very excited by these future opportunities. For example, the further efforts towards 3D, more photorealism towards 3D videos and photos so that you can actually use it in practice. So one thing that we miss here is the view-dependent effects, that we don't really model the view-dependent effects well. And complex and thin geometry, that is still a challenging problem. And also semi-transparent medium, that's glass or windows, that we really need to understand this better. Another part is that all we do currently is to reconstruct the original things, but we don't have flexibility to control manipulation of these visual data. And also, when we do the editing, there will be some associated regulation ethical issues such as deepfake. So this will require further efforts to do this. All right, so I want to conclude this with these are the reference talk about in this talk, and thank my sponsor to support our research, and I'll be happy to take questions. Thank you.
Thank you. There's one question. So, and if you guys have more, please put them in the chat, and we can definitely ask them. But the first question is, can 3D photos be generated from different viewpoints for simple photos clicked in front of white screens as a background?
Sorry, can you repeat that again?
Yeah. Can 3D photos be generated from different viewpoints for simple photos clicked in front of white screens as a background?
Yeah, I think you can, as long as you can estimate the main challenge is that you want to be able to estimate the depths. If you couldn't estimate the depths from single view very well, then your 3D photo would look weird. That's the potential limitation.
Awesome. Okay, here's another question is, what do you think of the point that depth estimation from a single RGB image is an ill-posed problem? I hear that estimated depth might not be very reliable, especially when you want to use it in a robotic scenario that has a high demand for precision.
Yeah, so you can think about like single view depth estimation because it's learning-based method. So it's usually if your testing scenarios is similar to the your training scenarios, then you typically will work better. But when you're at our outer domain scenarios, performance will degrade. They will give you plausible depths. What in the robust scenario, I think an important thing is that you are not just taking a photo and you make an action, right? You are sequentially taking multiple photos. You have a video stream, and you will actually as moving as you go. So it brings the question: do you really want the suite in just single input images, right? So you can actually use something like what we use for consistent video depths. Like we combine these multi-view geometric cues together with the data-driven prior that provided by the single image. These two combined can provide a much reliable depths. So that could potentially be used in robotics community in the future.
Awesome. Some of the attendees are asking, could you go back to the slide where all the papers are listed?
Yes, sure. Let's see. Yep.
Thank you. Okay, that seems to be all of the questions that we have today. So if that's it, thank you so much for this talk. It was really interesting, really cool stuff. And we really appreciate your time and, ending our seminar series on a high note. It's been a great semester, so thank you to everyone who attended. And a recording of this will be posted on Machine Learning Center's YouTube channel in the next week or so. So if you want to go back and look at anything that this was recorded and will be posted soon. But thank you guys, and I hope you have a great rest of your day.
All right. Thank you. Bye.